Is your life controlled by the little things? The butterfly effect is the idea that a tiny cause can have massive effects. A butterfly flaps its wings, and a tornado develops on the other side of the planet. Movies like Donnie Darko, The Butterfly Effect, and even this scene in Jurassic Park talks about it. But chaos may have more of an influence on your life than you think. So what is the math behind the little things? I'm actually Christine, and here's how it works. The fact that your actions have consequences isn't news, but what chain of events could waking up 1 minute early or ordering a medium coffee instead of a small have on your life in 20 years? How good are we really at predicting things? The butterfly effect is an aspect of chaos theory, and chaos theory is a branch of mathematics that deals with seemingly random or unpredictable behavior in systems that are governed by deterministic laws. Systems where end results can change pretty dramatically based on very small differences in initial conditions. Basically, little things have big consequences. Math and science can predict just about anything. That's their whole thing. Tests are full of those kinds of questions. If a man with 100 oranges adds 500 watermelons to his wagon, how fast will it tumble down this hill? We are, for the most part, pretty good at calculating the future. So why is chaos theory so difficult? Over the years, people like Sir Isaac Newton and Henri Poincaré have caught glimpses of chaos theory, but it wasn't really until the 1960s when Edward Lorenz, a professor at MIT, performed the first real experiment with weather. Using weather systems to study and illustrate chaos theory is actually pretty clever because it's something that most people can easily understand. We all know the struggle of trying to predict the weather a week out. Sure, we're pretty confident it won't rain this weekend, but you know that sunny sky forecast the weekend after is like 50-50 at best, because there are a lot of moving parts in the atmosphere. Lorenz made a computer simulation using things like pressure and humidity to predict the weather, like any meteorologist. The computer would print out a row of numbers with the final outcome. At some point, Lorenz wanted another simulation real quick, so he started halfway from a previous printout, and the final results from that came out totally different. Instead of a sunny day, for example, it was saying clouds and rain. The reason this happened is because the printer rounded to 3 decimal places, but the computer used 6. So when he entered the numbers from the halfway point, it was a difference of less than 1,000th, but it was enough to give completely different results. This is a core component of chaos theory, sensitivity to initial conditions. Chaos theory isn't random, by the way. Random and chaos are two very different things in mathematics. Chaos systems appear random, but there are underlying rules. Random, on the other hand, isn't just a concept we use to imply that we didn't see something coming, or a personality trait where like, oh my god, they're so random. It has different definitions in different fields, and it is a hotly debated topic. What is random? Can there be true randomness? A random number generator on your phone, for example, isn't truly random because it's using an algorithm. There is no equation for generating randomness. We just mimic it as best as we can. And to be honest, we don't have a good eye for it anyway. In 2005, Steve Jobs released the iPod Shuffle, which played music randomly for the first time. Everyone loved the idea, but people complained that it wasn't random enough because maybe 2 songs by the same artist would play back to back. That technically could be random, but people don't want random. They want diversity. So Apple programmed the music to be more spread out and avoid human recognizable patterns. They made it feel more random by actually making it less random. Another example is a coin toss. It looks random, but it is following Newton's laws. If we had all the minute information from wind resistance to the coin's weight down to the infinite decimal point, then we would be able to predict which side the coin will land every single time. But we don't know how to get all that. Not to mention, it's possible that we wouldn't even be able to recognize a truly random number or system if we saw it. So the next time someone says, oh my god, they're so random, trust me, there's a pattern. One of the fundamental assumptions in classical physics, the kind you learned in high school, not quantum physics, that's a whole other thing, is that nature is deterministic, meaning that if you know absolutely everything about a system, you can predict the future of that system. If I throw a ball, I only need a few pieces of information like speed and mass to determine where the ball is going to land. The challenge with chaotic systems is that we don't know everything about them, so we can't enter all the necessary information to know what the future is going to be. It's not just weather that has this quality, even our solar system is chaotic. In 1687, when Sir Isaac Newton published his Principia, with its equations for gravity and motion, it seemed like anything could be predicted. But Newton knew something was a bit off. His equations for the motion of celestial bodies didn't cover everything. It only worked for two bodies. This is known as the n-body problem. The n is a placeholder, so it can be 3 celestial bodies like a 3-body problem, or it could be 1 star, 4 planets, and 5 moons and be a 10-body problem. Calculating the motion of 2 bodies in space like Earth and the Sun is pretty easy. It's once you add another body though, like the moon, where things begin to change. In 2009, researchers at the Paris Observatory ran 2,501 computer simulations of different planetary orbits in our solar system. They wanted to know where each planet would be 5 billion years out. The only difference between the simulations was the distance between Mercury and the Sun, which they changed by less than a millimeter from one simulation to the next. A millimeter. And yet they found that in roughly 1% of the simulations, Mercury's orbit changed so dramatically over time that it could eventually collide into the Sun or Venus. There was even one simulation where Mercury threw the entire inner solar system out of whack. This doesn't mean that Earth is going to be thrown out of the solar system. We're pretty confident we're good for at least the next 100 million years, but it isn't a certainty. Interestingly enough though, there are some solutions to the n-body problem. Researchers in China discovered 1,223 of them by testing 16 million specific orbits with a supercomputer. But there is no general equation that can exactly predict the motion of any 3 or more bodies. If you Google chaos theory, you'll see this image a lot. This is called a Lorenz attractor, and it's based off that weather study from Edward Lorenz. He simplified the equations from his simulation and simplified them again and again until eventually he got these 3. These equations have 3 variables, which means they can be plotted in 3 dimensions. So this isn't flat like what you'd see on a Steve Kornacki graph. This is a 3D space, so there's a left and a right, but also a forward and back. Using these equations, Lorenz chose some starting points, entered them into his computer, and got an image like this. The line never intersects itself or retraces its own path, and it goes on forever. Sometimes it can even stay on one side a bunch of times before crossing over and then just jumping right back again. The points don't connect to form a perfect loop, because if they did, then it would loop forever and the system would be predictable. This is a picture of chaos, and yet there is order to it. If we wanted to have simulations and have them all end with the same exact result, we would need to enter the initial information with perfect accuracy, so to the infinite decimal point. Then the end results would be exactly the same, but we can't do that. Even a millionth of a billionth difference gives us a totally different final state. This is an image of that, different initial conditions in motion evolving over time. The points move toward a shape which coincidentally here looks like a butterfly. That is the attractor. An attractor is a state that the system eventually evolves to over time. There are different kinds of attractors, but in Lorenz's case, it looks a lot like a butterfly. This isn't an all-encompassing image of chaos theory, by the way. This doesn't take into account the location of things or really anything else. This is just a basic illustration of the effects of small disturbances. So how does this all affect you? Well, we don't know. It's perfectly possible that every little decision you make leads to drastically different outcomes. That the movement of the neurons in your brain or the sand beneath your feet is leading to different futures. Determinism tends to make people question free will and destiny. How much of it is science and how much of it is human? Do we have free will, or are the wheels of destiny already in motion and we're just unwittingly drumming along? I think people like the butterfly effect and chaos theory in general because it gives us a feeling that what we do matters, that the little decisions we make could have an impact on the world, and that maybe it is all connected.